Okay, I'll just, yeah, all right. This one. Maybe not. Hello, everyone, and welcome back to Quantum Information Science and Technology Colloquium. Today, we are very happy to host Professor Andreas Wallraff from ETH Zurich. Professor Wallraff did his undergrad at the University of Aachen and the Imperial Military College. And then he did his PhD at the University of Erlangen, continuing his work as a postdoctoral fellow at Yale University. There he was at the center of a really new field that was building artificial atoms in the superconducting platform. And that really gave rise to a lot of interesting results in the field called circuit QED, as well as what we know now as the superconducting quantum computing platform. Today we will hear about some impressive technology they have built at ETH to test them inequality. Thank you.
All right, so thank you very much. The host lets me know that the meeting is being recorded, and therefore my slide doesn't work. All right, so thank you very much. Thank you, Marina, for the invitation. Thank you for coming to this presentation or to this colloquium here. So on the title slide, you see something that looks a little bit like a particle physics experiment, but it's actually a quantum information processing experiment with superconducting circuits. And so the title of my talk is a loophole-free Bell inequality violation with superconducting circuits. And for me, this is actually a first, because I haven't presented this work myself yet to anyone. So you're kind of the first guys who will hear about it, at least from me directly. So it's been a long project. We've essentially been working on this for almost 10 years. I just noticed since I wrote up this project. And so here you see the team of people who work on it. So it has a larger team of experimentalists at ETH Zurich. And we've collaborated both with sort of quantum information theorists and also with Alexandre Blaise's group at the University of Sherbrooke, who's kind of an expert on the theory of circuit QED. And since you see there's a big experimental apparatus involved, we also had a strong engineering team that helped us on this project, as well as a team from Spain that built quantum random number generators for us that we used in this project here. And it's been supported by various funding agencies, but I should call out in Europe, there's a nice one. There's the European Research Council that gives nice large grants to single PIs to do kind of challenging projects. I would, in addition to the people who are on the title slide and who did this experimental work, I also would want to give a shout out for all the students and postdocs who have worked with our lab in the past now 16 years at ETH Zurich. And maybe it's also curious for you to see what they now do. And I think there's a nice mix of people who have their faculty positions at many different places, including Stanford and Oxford University and also Chicago. And there's also quite a few students students and postdocs who now work with either startup companies in quantum information science or companies that provide tools in and around quantum information science. So I'm grateful to everyone and their contributions to getting our lab where it is today. Good. So I think I've picked up a timely topic. So when Marina asked me about, okay, what should I talk about when I'm here, I figured, yes, Marina has seen this experiment live in our lab, and so I at least the experiment was set up, and I figured that this is the right topic to talk about. And I think we agreed on that topic before we knew that there would be a Nobel Prize in physics essentially on this topic. So this Nobel Prize in physics this year did go to three people: Anna Aspe, John Clauser, and Anton Seininger. And here you see sort of the short version announcing the Nobel Prize, and that the Nobel Prize in Physics in 2022 was awarded jointly to these three scientists for experiments with entangled photons, establishing the violation of Bell inequalities and pioneering quantum information science. And yeah, the work today that I'll present to you is doing a loophole-free violation of Bell inequalities with superconducting circuits, which is the first time that such an experiment has been realized. So maybe for the backdrop, so why are Bell tests sort of interesting? I think the interest in Bell tests developed around this weird feature of quantum mechanics, that quantum mechanical objects seem to have these non-local properties. Everything else we know about physics of the world around us seems to obey these rules of locality, namely that events can only be influenced by actions in their past light cone. So here you see such a space-time diagram, sort of space in these two dimensions here and time along an orthogonal direction. And what this means is that any properties of an object in space can only physically have interacted with other objects at prior times in this past light cone. And all the objects in the past light cone could interact with that object at that point in time and space if they were close enough to that object so that any interaction with that object could have propagated at the speed of light towards this particular point in time. Yeah, and if you had another object that was just too far away from this point in space, just any physical interaction with that point in space couldn't have mattered, because all physical interactions are mediated by forces that are mediated by particles. For example, if it's the electromagnetic interaction, those forces are mediated by photons, and these photons need to actually travel between two objects in space to mediate that particular interaction, and they can travel faster than the speed of light. And so now in quantum physics, there's this question: when you create a pair of entangled particles, those particles are entangled with each other, and then when you perform a measurement on this pair of entangled particles, there are correlations between the measurement outcomes that seem to exist instantaneously. So these correlations couldn't be mediated by any interaction that would be traveling at maximum at the speed of light. So that it needs to be a property that is somehow imprinted on these two particles through their quantum mechanical behavior. And that people found kind of very weird in the beginning of in the foundational moments of quantum physics or quantum mechanics. And they were sort of unhappy about that. In particular, Albert Einstein was unhappy about that, and with his collaborators, he kind of thought about this problem, and he kind of thought that something was wrong or incomplete about quantum physics itself. So that maybe the description of the world around us in terms of quantum physics might have been incomplete in some form, and then we were missing some further deeper insight into the nature of quantum physics that would maybe explain how correlations would come about between entangled particles. So, and there were lots of discussions about this, and it seems like an almost philosophical level discussion about the interpretation of sort of the nature around us. And you could read this original paper by Einstein, Podolsky, and Rosen that was pointing out this problem, and that led then to a debate between Einstein and Bohr about the interpretation of quantum physics. And so things then changed. So this seemed like a very much like an almost philosophical discussion. But in 1964, John Bell, who was a scientist at CERN, the particle physics laboratory in Europe, he kind of thought about the problem and came up with a criterion, the so-called Bell inequality, that would allow you to test if you had an entangled pair of particles to perform a measurement on them that could test whether the physics of these particles were described by some sort of local realistic theory, where like the arguments that I just had put forward apply, or that the properties of the particles would be described by quantum physics. And so that led to this definition of a test that you could use to see whether quantum physics was the theory that actually would need to be used to describe the properties of entangled quantum mechanical particles. And so this is then a fundamental test of quantum physics of big importance. And I think this is the reason why, or one of the reasons why the Nobel Prize was awarded to the three scientists that I just mentioned before. And if John Bell would have been still around, or he would certainly have been one of the three laureates there, and maybe they would have gotten the prize much earlier if John Bell wouldn't have passed away. So there's this sort of fundamental importance of doing a Bell test to just confirm that quantum theory is the right way to describe the properties of quantum mechanical particles. But you could ask yourself, is there anything else that is important about the Bell test? Is there any sort of useful aspect to it rather than testing, in some sense, only the properties of the quantum physical nature around us? And yes, there is. So these Bell tests are this feature of non-locality of quantum mechanical particles, could also be used as a resource in quantum information processing. And there's different application areas that derive from that. So one is that you could use these so-called Bell tests that I explain how they work in a little bit to perform an independent verification of the performance of quantum devices and quantum networks. So somebody could give you a physical system, and you could run a Bell test on it, and you could verify the operation of that device sort of independently of as many other assumptions as possible. So then this Bell test and non-locality can be used in secure communications, namely in quantum key distribution. And there's a sort of a special subfield of that, which is known as sort of device-independent quantum key distribution, where you could verify that this quantum key distribution is secure, even though that you know nothing about the inner functionality of the device itself. And then there's a set of other interesting applications that use Bell tests and their non-local or their loophole-free versions that can be used to create randomness. You could ask yourself, okay, where is randomness needed? For example, if you run a casino or so, you might want to have access to some randomness. If you do quantum Monte Carlo or Monte Carlo simulations, you want to have randomness available. And you could ask yourself, okay, can you assert that a random bit string is random, and how would you guarantee that? And Bell tests can be used to make sort of certifiable random numbers, and to also improve the randomness of a certain set of random numbers that might have been handed to you. So there's not only this fundamental interest, but there's also applications of loophole-free Bell tests along these lines. So what is a Bell test? So in a Bell test, there's typically two parties, sometimes you call them Alice and Bob, and these two particles take hold of two quantum mechanical objects. And those could be qubits, for example. And the first thing that they do is they prepare an entangled state between the two qubits, and you've all heard quantum information processing lectures, and so you know about entangled states. So here's an example for such an entangled state between two qubits, where they're in the entangled state that can be described as GG, both of the qubits in the ground state, but both of the qubits in the excited state over square root of 2. And what this means, when you would now go ahead and measure these two quantum bits, you would find both of them in the ground state, or both of them in the excited state, but never do you find one in the ground state and the other in the excited state. And when you perform a measurement on this quantum mechanical entangled object here, You don't know which of the outcomes we find, whether the two qubits are in the ground state or in the excited state. Both possibilities exist with a probability of a half. But if you find one of the qubits in the ground state, you can assert that the other qubit is always in the ground state as well. Or if one of them is in the excited state, you can assert that the other one is in the excited state as well. And that is independent of the physical separation between the quantum objects. So in the Bell test, you start out with preparing this non-local entangled state. Then in a second step for performing a Bell test, you actually make a decision on what type of measurement you should be performing. And so you randomly select a local measurement basis for your two quantum systems. And so this local measurement basis choice here you describe as a measurement basis A for one of the qubits and a measurement basis B for the other qubit, which you could implement in two different ways. And so this measurement basis choice actually happens at the very beginning of your Bell test after you have prepared the entangled state between the two qubits. And here you see a picture of how you could imagine that basis choice. Say for each one of the two qubits, you either measure along this axis A or along the axis A prime, and you choose between these two axes randomly. The second qubit you measure either along the axis B or along the axis B prime, and again you choose which one of those axes you measure along randomly at the beginning of the Bell test. And this random basis choice you realize sort of with a randomness generator and preferably with an as ideal as possible randomness generator. And this random number generator picks the measurement axis along which you measure either one of the two qubits that are entangled with each other. And then you read out the state of both qubits which are entangled and which are possibly at a large distance from each other, and you record the value of the measurement. And if you perform a measurement of the qubit along the computational basis, you could have essentially, or on any basis for that matter, you can essentially have two outcomes. Yeah, the qubit state could be either along that measurement basis or opposite to that, with a probability that is characteristic for the measured state. And so what in a Bell test, what you record is the choice of measurement basis, whether you have measured in B or B prime, that we write down here as the two choices 0 or 1. And this you can do for qubits for this choice A or for the choice B, where A is the measurement basis for the qubit A, and B is the measurement basis for qubit B. And then you perform a measurement which can have two outcomes, either parallel to that measurement axis or anti-parallel. And then you repeat these three steps for a large number of times, and you try to characterize the measurement outcomes that get created by that procedure. And for that purpose, Clauser, Horn, Shimoni, and Holt had defined like a quantity that is called the S value that you can calculate from these measurement outcomes here. And the quantity that you determine is you take the measurement outcome of one of the qubits X and the measurement outcome of the other qubit Y for the basis choice of the two qubits labeled A and B. And so there's two basis choices, either B and B prime or A and A prime, that are labeled 0 or 1 here. And so this here, the brackets indicate that you take an average over all the measurements that you have performed. And then this S value that Clauser, Horn, Shimon, and Holt have defined is the following quantity here. There's 4 combinations of these measurement bases, 0, 0, 0, 1, 1, 0, and 1, 1. And for each one of these 4 measurement basis choices, you calculate the expectation value of the measurement outcome of X times the measurement outcome of Y. And you calculate this quantity here. And now it turns out, sort of, if if your particles were governed by local realistic theory, this S value here would be bounded by a maximum of 2. When the particles behave quantum mechanically, though, this S value can have a value of larger than 2, and its maximum can be up to 2 times square root of 2. And so now you have a quantity that you can measure that can actually tell you whether your two particles behave according to some classical local realistic theory or according to quantum theory. And so now there is a real test that can tell you whether the physics of these particles is described by quantum physics or maybe some other classical local realist theory. And this particular formulation was first put together by these 4 people, where Clauser got the Nobel Prize, and which is a version of this original argument that Bell had formulated. So this is the basic formulation of what you do in any type of Bell test. So maybe that's a good moment if you have any question or so, you could ask it right now, because that's essential for the presentation. Yes.
So just like average out of many
So the question is, are these averaged about as many runs as you can get? And the answer is yes. You have, for every individual run, you get an individual result. Yeah. So in an individual result, you pick, or your random number generator picks 2 measurement bases, and you get 2 results, plus or minus 1 for each one of the 2 qubits. You multiply those with each other, you write them down, and then you repeat. And then in the end, you have a long list of products of plus and minus 1 that occur when you pick A or A prime or B or B prime basis, and then you average over all of the ones that you got, and then you calculate this S value. So you get one S value for the ensemble of your data. And the more data you take, the more certain you are about the actual S value that you have measured, and there will be a statistical distribution around it, with some mean value and some width. And then you can determine, like, when you find some S value that is larger than 2, how large is the statistical significance of that? Any other question? Good. So if you have any other question later, you can also ask it later. So what about loopholes in this Bell test protocol? So there's a number of loopholes. So maybe what Anna Aspe, for example, thinks is the most important loophole is the so-called locality loophole. So to close the locality loophole, you would need to perform experiments with space-like separation between the entangled qubits being measured and the events defining the basis choice. So what does that mean? So I talked about locality on this introductory slide. So say if the 2 particles are too close to each other, and it takes you a finite amount of time to measure that state, in principle, you could come up with a theory where some physical interaction mechanism communicates between one of the particles and the other particles in which basis it was measured. Yeah? And this is possible when your measurement takes longer than it takes light to propagate from one particle to the other. But now, and if you believe in relativity, then you would say sort of no influence could propagate faster than the speed of light. And if you separate the particles by a large enough distance, you can make sure that there is no physical mechanism that could actually have the 2 particles somehow interact with each other to essentially explain the correlations that would arise when you perform a measurement on the tube. So closing the locality loophole means that you need to separate your 2 entangled particles by a large enough distance. And that's actually the thing that is very difficult with superconducting qubits, because they typically live in a cryostat, and if you want to separate them by many meters, many tens of meters, many hundreds of meters, you need to figure out how you would do that while being able to still entangle them with each other. So that's one of the loopholes. So then there's a so-called detection loophole. So these Bell test experiments, they were typically in the beginning performed on photons, optical frequency photons. And until sort of reasonably recently, so maybe around 10 years ago now, efficiency of individual photon detectors was kind of poor. Yeah? So when you would send a photon towards the detector, the likelihood of actually detecting it was sort of small. That was maybe a few percent or maybe then a few tenths of percent, but it was never large at a level that you could with high certainty say with a probability of larger than 2/3 detect the state of that particular photon. And why is that a problem? This is a problem because if you were not detecting all of the entangled particles, you could argue that maybe you can determine the properties of the particles which you did detect, but what about the properties of all the other particles that you didn't detect? Yeah? So it could be that the other particles that you didn't detect behave to some other law of physics, yeah? And you couldn't, in principle, exclude that. And so therefore, early experiments on Bell tests required sort of the fair sampling assumption, namely that the particles that you actually detected were behaving like the average of the other particles. But you can exclude that if you're able to really measure all entangled pairs that you've ever created. And then finally, there's a loophole that is known as the freedom of choice loophole or the measurement independence argument. And that requires that you need to choose the measurement basis for your two qubits in a statistically independent way from the qubits and also their measurement devices. So this is maybe a loophole that one can argue about because, for example, in principle, you couldn't exclude that somehow we live in a physical world where everything is entangled with everything else and all our future is all predetermined by some interactions that we all had in the past. So you could maybe say that there's sort of two random number generators here, but it could be by some other physical mechanism in their common past they have interacted in a way that sort of predetermined the random numbers that these random number generators would create. And this is something that, I mean, on principle grounds, you can't exclude, but you try to do your best job for creating these random basis choices. So these are the main loopholes that you need to close. And it was actually quite difficult for experiments to address those loopholes. So you remember this argument from Bell that was first communicated in '64. And then there was this first experiment by John Clauser and Friedman in '72. So it took already 8 years to do an experiment at all. And then Alain Aspect in France did actually a second set of experiments 18 years after this proposal by John Bell and 10 years after the first experiments by John Clauser. And all of these initial experiments, they relied on any of these additional assumptions. So they left open some of the loopholes, which I just described. Sort of the entangled particles were not sufficiently separated from each other. They didn't detect all of the events that were created. And they didn't choose their measurement spaces randomly. And so then between '82 and sometime in 2015, many steps were taken towards successively closing all these loopholes. And maybe one aspect that one review or short article, which is only 3 pages long, that is nice to read, is this article of Alain Aspect in the American Physical Society journal, which is called Physics, which on 3 pages discusses the history of Bell tests and the different steps. So that's something that is interesting to read. So if you look at that, so this was 18 years after Bell's inequality was formulated. And then in 2012, in our lab, we thought like, okay, so there's still no loophole-free Bell test at all with any system. And so we thought that, okay, we could do one with superconducting circuits that would work. And the outcome of that, I would like to show to you today. But unfortunately, it took us the better part of the 10 years that followed to actually make it work. Yeah, while I was in 2012, I was pretty convinced that we could make that work. And so, like unfortunately or fortunately, depending on how you see that, in the meantime, there were successful loophole-free Bell test experiments by a number of groups, by Ronald Hansen's group with NV centers at Delft, by Anton Seidinger's group with photons in Vienna, and by a group at NIST in the US with photons in 2015. So at that moment, you could have said, okay, you could fold and just not do the experiment. But I really liked it, and we had started already, so we figured that we should do it anyhow. And so that's what we embarked on. And I still think it's pretty interesting, and it's also special because like all of these systems here are either NV centers, photons, neutral atoms, or there's also experiments with ions. But there's no experiments with loophole-free experiments with superconducting circuits, nor with any other sort of solid state-based system, and the exception of NV centers, which are microscopic degrees of freedom in defects and diamonds, essentially. Okay, so what do you need for doing a successful experiment with superconducting circuits? So first, you need to be able to violate this CHSH inequality. And for that to work, you need to make good entangled states, and you need to be able to read out the qubits that are part of these entangled states with high fidelity. So that's one of the requirements. Then you need to guarantee this measurement independence. You need to choose your basis randomly. And this is also something that initially, before these other experiments came about, that with loophole-free Bell tests, we weren't really counting on doing this, because it's kind of complicated, costs extra money, extra time. And we were a little bit annoyed about that initially because it made our experiment more complicated, but that's something that you now need to do a state-of-the-art Bell test. Then you want to close the detection loophole. That is very simple for superconducting circuits. So closing the detection loophole means that every time you create an entangled state, you need to measure the two qubits, and you need to know their state with high enough fidelity. And in superconducting circuits, that's easy. You do it all the time. Everyone who builds quantum computers with superconducting circuits does that. So it doesn't have this problem that experiments with photons have, where it's difficult to detect all the photons. And then maybe the hardest thing is to close this locality loophole, and maybe it shouldn't be the last point in this list because we asked Anna Speer about it. He tells you, okay, the locality loophole is really the thing that you should be looking for. And so you need to realize space-like separation between your two qubits. So what does it mean to realize space-like separation between your two qubits, which you entangle? So you can estimate what that means for superconducting circuit experiment. So we did research before to figure out how quickly we could read out the state of these superconducting circuits, and we figured that, and we demonstrated that we could do that well within 50 nanoseconds. Unfortunately, there's random basis choice here in the beginning that takes about 30 nanoseconds or so. And then maybe your signal propagate in your detection lines a little bit, and that takes maybe 20 nanoseconds. And so the total budget in time that you would have in mind is maybe to do 100 nanoseconds for this. You need 100 nanoseconds between the random basis choice and the end of your measurement to perform a Bell test. And so that then means that your two superconducting qubits who live at 10 millikelvin temperature need to be separated by 30 meters. And so now solution refrigerators that you buy are fairly big nowadays, but the maximum sort of linear distance that you have in a system like that now is maybe 1.5 meters or so. So you need to do something special to do 30-meter separation. So there's another requirement on I mentioned here sort of a bit vaguely that the fidelity of the entanglement needs to be high and the readout fidelity needs to be high as well. But you can sort of communicate that a bit more strictly. You could ask yourself, okay, what is the maximum Bell violation? So when this Bell parameter S is 2, then it's essentially classical. And the maximum value that it could take is 2 square root of 2. And this maximum value is now reduced when you have a finite fidelity for detecting the qubit states. So when the probability of identifying it correctly is different from 1. And it depends on the fidelity of the entangled state, which is expressed here in this entanglement measure, which is known as the concurrence. So on the right-hand side here, you see a plot where the S value is plotted here as these lines. The readout fidelity is on one axis and the concurrence on the other axis. So your your entangled state fidelity gets better this way, your readout fidelity gets better the other way. And if you want to violate Bell inequality, you need to be somewhere in this top right corner. And the better you are, the higher your S parameter will be. So now you could ask yourself whether you could be in that range with your hardware. And we had done experiments previously that we have also published, where we understood how good both our readout could be and how good the entangled state concurrence or fidelity could be. And so we verified that in a system where the qubit would be separated on a meter scale, we could get concurrences of about 0.76. And we could get readout fidelities of about 0.98. And that would maybe bring us into this upper right corner of this plot here, so that we could get an F value for this Bell inequality violation that is larger than 2, which is the thing that you need to show to demonstrate that your pair of entangled qubits actually violates the Bell inequality. So we are fairly confident that we would be able to do that, because we had done the right experiments already before. So maybe to some degree, if you look through our publication history, you'll find like papers that look maybe at times a bit like you would ask yourself, okay, why do these people look at this stuff? And in the end, when you know about this project, you can sort of put the pieces together and you see that maybe in the last 10 years we've done experiments that you all need to do to be able to violate this loophole-free Bell inequality. So how to close the locality loophole with superconducting circuits? So you could think about different ways how you would entangle your superconducting qubits and over a larger distance. And one approach that you could think of is you could entangle them using optical or telecom wavelength. Yeah, you could maybe convert the state of one of your qubits to an optical frequency photon, and then send that photon along some fiberglass thing to another cryostat, convert the optical photon back to a microwave photon, and entangle it with the other qubit. And that's all very nice, but it requires very good microwave to optics conversion and back. And this is something that lots of people kind of research now, but it's very, very difficult, and it's very difficult to get to the quality that you need. And so I think, for example, before you replace our 30-meter cryogenic microwave link with this, I think it will still take some extra time. And at the same time, like basic microwave frequency networking elements were actually realized by our lab and also by other labs. First, by taking qubits on 2 different chips in the same cryostat and entangling qubits, say, through a coaxial cable that goes from one chip to another chip. And then we ask ourselves, okay, if you had now your 2 chips in 2 different cryostats, 30 meters apart, how would you do that? And so what are the desired features of that? Say you have 2 cryostats that are separated by some distance. You want to have this link maybe operate at microwave frequencies, because in the end, that's the way how we do gates between qubits in our quantum computing chips. Yeah? Like if you look at how a quantum computer operates, you have essentially qubits in this quantum computer on a single chip, and they talk to each other by exchanging microwave photons through some waveguide, and typically this waveguide is maybe a few millimeters long, but all the protocols and things for that exist. And so now our idea was, okay, good, let's take such a microwave link, and instead of making it millimeters long, we make it tens of meters long. And then it's compatible with existing gate protocols. So and if you operate that link at millikelvin temperatures, it could be low loss. And interesting, maybe one of the interesting things is if you have a cold microwave frequency waveguide, the loss can be as low as the loss of a telecom fiber. You might say, okay, it's not quite as convenient because it needs to be cold, but the loss is still like less than a dB per kilometer. And also when it's cold, there's no thermal background in the connection between the 2 chips. And so what else do you want? You want it to cool down in a reasonable time. You don't want to build a cryostat that takes months to cool down. And you probably want it to be an extensible solution. So here's our concept for that. So this is a kind of a schematic of what a regular cryogenic system looks like. You have usually some vacuum can, and then there's radiation shields that are kept at different subsequently colder stages. And in the middle, at the end, at the lowest temperature stage, you have the chip that houses your qubit. And so our thought was now, okay, we just take this arrangement here and we just put a cryostat on the side and just build it to form a link to a second cryostat. And we essentially inherit all the parts, like all these radiation shields, but just build them up horizontally. And so here's a picture of that. So there's an aluminum waveguide in the center, all these radiation shields, and it sits in a vacuum can. And if you look at the side of such a module, so it comes in these 2.5 meter modules, and you can just put them together and fit them between your two cryostats and make it as long as you have money for. And like one of our students actually calculated that the cost per kilometer is not so different from the cost per kilometer for a highway or so. So if you wanted to put it next to a highway or so and have a longer distance, then you could do that. So you could have either like a 5 meter version or maybe a 10 meter version or something even longer. And so what are the problems? So you need to deal with the heat load, and maybe it's a cryogenic engineering problem, and it's kind of a nice one. So you can think about how to do that, and it depends on the thermal conductivity of the materials, on the heat load, and all of that. But in the end, it can be done. So we decided to build such a thing. So here's a picture of one. So here's one cryostat on the left, another cryostat on the right, and there's a 5 meter version here. So the 5 meter version has a chip with qubits sitting there, a chip with qubits sitting there. And here we demonstrated that you can entangle the two qubits there. You can send quantum bits from one chip to the other along this link. And so this got published 2 years ago. And so here we kind of emphasize that if you wanted to expand the capabilities of quantum computers, you could make little networks of quantum computers this way. So then we, and this seems a bit reversed. So this got published in 2020, and so here's a picture from 2019, and this was longer. So this was kind of a bit squeezed into our lab. So we had a lab that on one side is 10 meters long. So you can see one cryostat here and the other cryostat there, and sort of a 10 meter link there. And this 10 meters gives you sort of 33 nanoseconds or so. And so then, but I told you the time budget was not 30 nanoseconds, but 100 nanoseconds. So you need 30 meters. And so here's a CAD drawing of what this thing should look like. And so here's a little picture. And even though that I'm not doing so well in time, I will still play this video for you. So that's what our lab looks like. So Maria was there and actually looked at it. And so here you see this 2.5 meter modules. When you walk along the lab, it looks a little bit like a particle physics experiment. So then here in the middle, you see it needs an extra cooler that deals with the radiation load on the outermost shield to keep it cold enough. And so here, it's 15 meters, and in the center there runs a waveguide, and you see the other cryostat on the other end. So this has about 1.5 tons of copper in it, and it's assembled with 14,000 screws. Yeah, and it did take a moment to put them together. But it's a cold waveguide, and it really works well. Yeah? So is it now easier than building optics to microwave converters? I don't know, but it works better apparently. So like if you wanted to repeat this with optics to microwave converters, you probably couldn't. It would not be good enough. So that's a peek in the lab. So here's a profile of the cooling curves of the cryostat. So you see there's a cooler in the center and some at the end. And what maybe is a thing to look at. So this is so there's lots of temperature sensors in this system. So this is the temperature profile around the base, and the hottest point is in this kind of 30 meter long thing, and the center is 50 millikelvin. So it's essentially a cryostat that is 30 meters long, and it works well. And it takes 7 days to cool down or so. So how good is this waveguide? So here's this waveguide, which is just a WR90 waveguide. So that's an old fashioned, but it works really well. It's just an aluminum waveguide. We just bought it and we did nothing to it, no surface cleaning, nothing. And it sits in the center of these units, and it's kind of fixed here. And the other thing that is kind of funny, it's 30 meters long. And if you put it from room temperature to 50 millikelvin, it will actually contract like significant amounts. So it will contract many centimeters, and you need to sort of think about what to do about this mechanical contraction and how to compensate for it. And what is maybe interesting as a number is it will have loss of less than 1 dB per kilometer. So it's essentially like a good telecom fiber. So maybe some of you know better how good telecom fibers are, but I think this is roughly about what good telecom fibers allow you to do. And so we've also measured that mostly in a little characterization measurement. So we took a piece of waveguide, like 2.5 meters long, and we make a microwave resonator out of it and measure the quality factor of every one of these resonances. And essentially, without doing anything, it makes a resonator that on every resonance has a Q of 1,000,000. So, and if you wonder about it, if you, for example, go to a lab and try to put together resonators on an integrated silicon chip, or I think there's lots of mistakes that you can make, and you get things that are way worse than 1,000,000. And things that are simpler to put together in principle. Good, so I'll try to wrap it up. So how does this Bell test now work? So you start with preparing your entanglement. And so we have developed a protocol to do that. And that the way to do it was published in 2018. And that worked on a protocol that Andreas Wallraff had actually suggested 20 years ago at the time. And it creates a Bell state between these two qubits that sit in the two cryostats 30 meters apart. And we can create a Bell state with a fidelity of about 80.4% or so. And here's kind of a density matrix for this two-qubit Bell state. And the main source of infidelity for that is not the loss of the waveguide, but we have some elements in this waveguide, like some circulators, that actually are responsible for the main part of the infidelity here. So we believe that we could get the fidelity there up a fair bit in an upgrade of the experiment. Okay, so you create the entangled state essentially by emitting a photon from one of the qubits, transferring it to the other qubit, absorbing the photon there. And if you do that in a clever way, you can create an entangled state between the two qubits and the two cryostats. And how that works in detail, you can actually read up on in this Nature paper that is cited on the slide. And creating the entanglement is not part of the. It's a resource for this Bell test, but it's not actually one of the things that count for the time that you need for doing your Bell test. It's something that you do up front. So what then matters for your Bell test is you need to select this input bits that pick the random basis, and that takes about 17 nanoseconds in the random number generator that we purchased. And then from that moment on, you have 100 nanoseconds to finish the measurement of your qubits at the end. And so these random numbers that we generate control the measurement axes. I mentioned already how that works. And the measurement axis, the measurement basis choice, we actually realize by applying pi half pulses for qubits. And these pi half pulses get sent through wires to our qubits. And so there's a bit of signal propagation delay. And then the pulse has a finite length. So the propagation delay is 14 nanoseconds, the pulse length is 12 nanoseconds, and the random number generation time is 17 nanoseconds. And this here is our space time diagram, and these are the forward light cones of the events that pick the basis. So doing or not doing a pi half pulse on the qubit chooses between the B or B prime axis for the measurement, or the A and the A prime axis for the measurement. And then we finalize the Bell test by reading out the qubit state. And it's performing single shot qubit readout, and it takes about 15 nanoseconds. And we can do that with high readout fidelity, and that fidelity is about 98%. And it's documented in the paper here from 5 years ago. And then at the end, this readout signal needs to propagate to our detection electronics, the ADC. And when all the readout signal is absorbed in the ADC, this concludes the final point of our Bell test measurement. And that takes another 14 nanoseconds. And so when we measure the qubit state at the end, we assign a ground state measurement to value +1, or an excited state measurement to the value -1, and then we evaluate this CHSH inequality that I had mentioned to you. So we have gone through this slide here in quite some detail, and we calculate from 1 million repetitions of the experiment, we calculate that value and determine this S value and wonder whether it's smaller or larger than 2. Okay, and so this here then summarizes these experimental results that also wrap it up. So here's the experimental results. So there's in this CHSH value, there were 4 correlators for 4 different measurement basis combinations, 0, 0, 0, 1, 1, 0, and 1, 1. And you see these sinusoidal oscillations in these oscillations. Okay, and one thing that I forgot to mention is that there is a parameter that you can tune that is the relative orientation of the 2 measurement axes relative to each other, and that angle is measured or it's expressed as theta. And the Bell inequality gets violated for one particular or for a range of values, and the maximum violation is that theta is -pi quarter or 3/4 pi. So the contrast in these oscillations is slightly reduced from 1, and you can then calculate the CHSH value versus this control angle theta, and you see that it oscillates sinusoidally, and you see that it just a little bit passes the maximum value of 2 and at 2 angles, namely at -pi quarter and at 3/4 pi. And you can sort of compare that to what you would expect from master equation simulations, which are these dashed lines. And you can then zoom in these regions where the S value is larger than 2, and look at that with some finer steps in this control angle between the 2 measurement basis choices. And you see that there's a whole range of values of theta for which S is larger than 2 or smaller than -2. And in all this region here, then the Bell inequality is violated. And you could ask yourself how statistically relevant this is. And so we ran then a single experiment with 1 million repetitions at this particular value of theta here. And there we find that the S value is sort of 2.07. And you might say, oh, this is not much larger than 2. But you can then evaluate for this 1 million measurement what the sigma is. And the sigma turns out to be 22 sigma. Most of the other Bell inequality violations, I think people were typically happy with 6 sigma. So, and Andreas Wallraff in his paper, he described what, for example, what the particle physicists would consider sort of a statistically relevant violation of or statistically relevant experimental result. So this is 22 sigma accurate because we have enough statistics, and this took about a half hour to take this data. And if you're into statistics, also you can calculate the p-value, and the p-value is sort of small at a level that it probably doesn't even make sense to discuss that too much. So this is statistically relevant. Are you surprised? Were we surprised? No, we were not surprised. Yeah, but has anyone looked for a macroscopic quantum system whether it would violate Bell inequality or not? No, nobody has checked. So it's something that you should probably do. And it's not only that, but you can then also use this resource of non-locality in sort of algorithms that involve superconducting circuits sort of in some follow-up experiments. Good, and how are the loopholes addressed? So the freedom of choice loophole we addressed by choosing the measurement basis at random. The detection loophole was addressed by measuring all the entangled pairs that we've created, which is easy. The locality loophole we have addressed by separating our qubits by large enough. And then you could ask yourself, okay, by how much did we actually manage that the 2 measurement events were sort of space-like separated? And so the distance between the start and the stop events here, like our random number generators, is 32 meters and some, which we've measured accurately. And that creates a time budget for the Bell test of about 109 nanoseconds or so. And then if you measure the protocol duration or so, it was about 107 nanoseconds. So we have a 2 nanosecond margin, which is about 8 sigma. So for the locality loophole. And that's not a lot, but it compares roughly to what some of the other experiments have also achieved. So that needed to be accurate. And if you say that's too little, you could say, okay, let's get another 10 meters for the setup, which is not what I would suggest to be doing now, but if you want to increase the margin, you do that. All right, so I think we're already 5 minutes over. So this is the final slide. So how good or bad is that relative to other loophole-free Bell tests? So there's loophole-free Bell tests with photons, with NV centers, and with superconducting circuits. And the parameters that you could compare is like at what rate do you run this Bell violation? And sort of the photon experiments are very fast, but they have a very small violation. So if you think that, okay, 2.07 was not so great, sort of all of the other photon experiments, they have violations somewhere when you subtract 2 from the actual S value, you end up with anything of 10 to the minus, between 10 to the minus 5 and 10 to the minus 3. And our experiment had sort of 0.07 Bell violation. And some of the experiments with atoms or NV centers, they're significantly better there. But the repetition rate is usually much lower. And so our experiment is sort of in an interesting range where you have the largest violation at a good repetition rate. And that's sort of interesting for these applications like demonstrating quantum key distribution, randomness generation, and these other randomness protocols like randomness expansion or randomness amplification. And other things, other protocols that make use of non-local Bell tests, so loophole-free Bell tests. Good, yeah, and so there's maybe a range of things that you can do with the setup, both in terms of quantum information processing protocols. You could think about using these long waveguides to do waveguide quantum electrodynamics experiments. And one of the other motivations we had for setting up like multi-cryostat systems is to demonstrate basic building blocks for network quantum computing systems. Okay, with that, I'd like to thank you for your attention. And so this is a picture of our team that we took recently with many of our full-term project students, and inspired by the recent Nobel Prize, we thought about what we could do in our photo to demonstrate entangle. So that's what we came up with. So thank you very much, and so we're over time. But if you have some questions, I'm happy to answer them. All right. Thanks.
Thank you very much for this very interesting talk. I know some of you have to leave. Please sign in before you do. And now we're opening the floor for questions. Yeah.
This is more of a fun question, but how did Blueforce react when you said you wanted to order,
I think they gave us, we got a reasonable price for it. So they were not as interested as I hoped for. So as I said, we started this 10 years ago, and sort of in the meantime, Oxford Instruments also had a project with someone else in Germany doing something similar. And I really do think that Blueforce missed out on an opportunity to use this for some big time PR. So, but they were just not interested, and I think it was a mistake, but their choice. So I think they provided the client stuff. And the idea was that they would provide some engineering support, but in the end, I think this was mostly a thing that we did in our lab.
Okay.
If you were to expand the chamber to instead of 30 feet to like 50, 100 feet, how would that?
It's meters.
How would that?
It was 100 feet then.
How would that affect the measurement of the expanding?
Yeah. So this creates so essentially the loss in this waveguide itself has insignificant contribution to the fidelity of the entangled state that we create. So we could make it much longer, and the fidelity of the entangled state should be similar or close to identical, and it would give us more timing margin for the experiment. Now it was sort of squeezed into a phase-like separation as a margin of a few nanoseconds. Then if we would take 60 meters, then the margin would be 100 nanoseconds instead of 2 nanoseconds, because everything else would essentially happen in exactly the same way. Only the space-like separation would be bigger. And what we would need is you need twice as many units, so somebody has to assemble another 40,000 screws with 1.5 tons of copper, and you would likely need 2 more of these intermediate coolers. And I do think that likely the innermost stages would still be cooled effectively, because the heat capacity of all these materials at these low temperatures is quite small, and the radiation load from these radiation shields at higher temperatures is actually fairly small then. And you could probably still get away with just 2 dilution refrigerators at the end, but we have kind of, you can do thermal modeling for that and see what you need. So as I said, this I think you could build one along a highway if you wanted to, if you had enough money and were really motivated, or if you come up with a really good fundamental science wheel. So I don't know, that's just nothing real, but if you would say, hey, this is the way to detect gravity waves or something else that you're curious about, and you're motivated enough, I think this is not sort of crazy expensive in comparison to some other science projects that get done.
Is there something conceptual to learn from the fact that your qubits are actually coherent states of billions of electrons rather than microscopic degrees?
Yes, so I think this was one of the, for example, if you ask yourself what is different in this experiment than with the kind of the Bell test with photons or NV centers or with ions, so here the qubits are sort of macroscopic degrees of freedom, so they involve like macroscopic currents and large numbers of electrons, and in the mid 80s there was this question whether these circuits would show quantum properties at all, or whether there would be maybe sort of some fundamental physical aspects that would prevent quantum mechanics to kind of hold true for this. And there was not really, and people were really looking at that. Tony Leggett, for example, was looking very carefully at whether he could make out any reasons for why coherent quantum physics should not be observable. And if you look for sort of a fundamental question that it would address, is that this experiment now shows that you can do also sort of this very stringent tests of quantum mechanics also with macroscopic objects. And then how you define macroscopicity is maybe a bit of a question. There's also like Markus Arndt in Vienna. He tries to do this kind of interference experiments with double slits and large molecules or even organic materials. And you can try to test fundamental aspects of physics in this other domain. And I would indeed say that what you mentioned makes sense. So this is kind of a superconducting circuits are quantum systems that are not in this microscopic category. They're sort of macroscopic to some degree, and so therefore it's sort of interesting to do these kinds of physics with a macroscopic object.
Any question here?
Are the units isolated from each other? For example, if you go on a highway and it's only ever takes out one section, you have to repressurize the whole thing.
That's a good question. So we've actually been thinking about that. So for example, say if you're less in the context that you mentioned now, but say if you were, say there was a computer center and you have a network of quantum computers and they sit in a cryostat each, and you have these links between them, and you find out that you need to service one of your chips for some reason, and what you can do to take this apart in a reasonable way. So this has no reasonable way to do it. It's all one vacuum system. It's not isolated from each other, but if you really wanted to, you could think about how you would make this modular in a way that it can sort of seal off parts from other parts to deal with that. And that's certainly something that we've thought a little bit about, but we've not built any demos or so, but it's an interesting question.
And having this in a parking garage, or adjacent to the parking garage, it raises the question of from traffic.
Yeah, no, so it's on a, so the, so we needed to find a spot at ETH to set this up, and ETH is currently crowded at a level that you can't take like 40 meters worth of 40 meter linear length worth of lab space somewhere. So and this was actually built behind the ETH parking garage, so in an area where there were storage spaces, and so they just removed all the storage, or like a fraction of the storage space, and then we have a sort of a 40 meters long lab, and you saw the video, and the room is essentially, I don't know, 3 meters wide, but 45 meters long. Also, but the drum drivers are on the other side, so.
Any more questions? Yeah, let's say Victoria.
I have a question about the S value. Is there physical meaning to the value that, because you get above 2, so if there are hidden variables, then they are not local. But then can we learn something by the number that you get that is like less than square root of 2?
About the types of theories that you exclude, I don't think so. There's some operational. So, for example, if you like the level to which you violate the Bell inequality is useful when you want to use kind of the outcomes of the Bell measurement for something else. Yeah, like for example, in these randomness amplification protocols, it matters how much the violation is. So it might be some protocols perform better when the violation is strong rather than when it's weak. But in terms of types of theoretical models that can be excluded, I think in this original Bell argument, it depends on you have sort of conditional probabilities for measurement outcomes depending on measurement choices, and when these probabilities are kind of local, so when the measurement outcome is only influenced by the local measurement choices or so, that constrains the S value to less than 2. And I'm also not in I'm also not an expert on sort of hidden variable theories or so, because honestly, if you ask me, did I expect this to show up with something that surprised us? Probably not. I expected that this would work. And so I didn't really look with lots of seriousness on what these alternative models are.
So what are your students and the latency here?
So it's transmon qubits, and the coherence is okay, but not spectacular. Let me see if I find a picture. So there. So here's the qubit. So here's that's the island of the transmon. So here's a squid with a flux line. So I said nothing about the qubits essentially, and how it's actually done. So on the left hand side there's a set of readout resonator and Purcell filter for performing the high fidelity and fast readout. And on the right hand side there's a copy of that again with the emission resonator and the Purcell filter, and the photons get emitted this way into the waveguide. And there's a coax cable between the chipset and a sample mount. There's a bit of waveguide on the PC board, and then a coaxial line that goes into the waveguide. And the coherence properties are okay, but not spectacular. But does it matter? This kind of the entanglement protocol, I think it does 2 qubit gate, like say essentially 1 2 qubit gate by emitting a photon and reabsorbing, and then that's fast. And the delay time before we do the measurement is sort of short on a 100 nanosecond time scale, and the coherences or the energy relaxation times are around 10 microseconds or better, and the dephasing times are similar. So that's kind of fine. It could be a little bit better with better coherences, and we would not mind to have these devices better, but they're not our best ones. And one of the reasons is that the cryostat is a bit complicated in which this is set up. So another thing that we didn't quite see is what to get this space-like separation. We actually pull out cables on the bottom of the cryostat to the side. So you saw that there were the excite ports on the cryostat. So we have lines that go from there to our detection electronics to not lose space-like separation by having kind of cables go out of the top of the cryostat. And so there are things like that matter and that make it a bit harder to get to do good magnetic shielding and also good IR shielding.
All right, well, there's one question, and then we're going to wrap up.
So this experiment is not only showing the with some technical angles in between them. So experimenting how you implement it.
So the question is about how you adjust the angle. So there's two angles that there's the measurement basis choice, which is essentially choosing between two orthogonal angles. And whatever one of the bases is, you can turn the basis into an orthogonal one by applying a pi half pulse to your qubit, and that's what we do. And so you were asking about sort of these, you change between D and D prime or an A prime by applying a pi half pulse or not. And this angle theta, you actually rotate between your two qubits by having sort of and at the end of our entangled state generation, we can apply a single qubit rotation that kind of turns the two measurement bases relative to each other in a continuous fashion. And when we start the experiment, we have no idea what theta is. It's two experiments which are 30 meters apart from each other, and we don't know their relative phases initially. And so we then rotate theta once through 360 degrees, and we check for which values of theta actually our Bell inequality is maximally violated. And that establishes the phase relation between the two measurement bases. Through okay, good. So that's so one of the aspects that is important is that the two setups need to have a phase reference. Yeah, so they need to decide, or they need to have a stable relative phase with each other. And so one of the technical problems was that we have these two setups which are 30 meters apart from each other, and you need to have a phase stable reference for both of them across 30 meters, so that essentially the local clocks in the two setups run exactly the same way. And once they do that, you can just apply a single qubit rotation on one of the qubits to turn its measurement basis by an angle theta relative to the other measurement basis. That's all that needs to be done. So you can, I think in your single, it's a single qubit block vector that you choose, and your measurement axis you can essentially choose to your liking, and you can, like in any tomography experiment, rather than turning everything, say, from the Z into the X basis, you can also turn it from the Z into the X basis minus some other angle, and that you do by single qubit rotations.
All right, so with that, let's thank our speakers.